In this lesson, we're going to have a look at the wash sequence manager and what the differences are between managing this in ladder and managing it in structured text. So in the previous lesson, we went through the filtration sequence manager, which was all written in ladder. But in this one, the wash sequence manager, it's written in SCL. And whilst the structure and overall outcome of the code is the same in terms of how we manage it, there are some obvious differences to the approach because of the language that it's written in. So let's just refresh ourselves with exactly what's supposed to be happening in this sequence. So wash mode is a little bit more complicated than all of the other modes because it's made up of an overall governing wash sequence, which is everything that you see here, and then small key areas that provide specific functions such as air scour, backwash, top wash, and rinse. And there are loads of different ways you could approach this. You could have air scour, backwash, top wash, and rinse in their own mini sequences that the main sequence calls, or you can do what I've done, which is just leave a comment, say this section is for air scour, this section is for backwash, and go about it like that. I would say that if any of these subsections had maybe more than 10 steps in or more than 5 steps in, that I would probably create a function or a dedicated block for that particular part of the sequence. But because none of them are used more than once, so they're not repeated, and because they're fairly small, I didn't see the value in actually containerizing those in the code. So let's just run through what's happening. So in wash mode, the way it is started is it's called called to run in wash mode. There's two ways that can happen. They're not actually on this diagram, but they're either called from filtration mode or they're called from an operator pressing the start button for wash mode or a manual wash. So we're doing the check to say, are we currently in filtration mode? If we are, then we need to initiate a shutdown of filtration mode. That's usually handled or will be handled by the filtration sequence itself, because we wouldn't be calling wash mode if we didn't already know that we needed to shut down. So that's handled outside of the sequence. All that we're doing is the filter shut down? If it's shut down, then yes, we can proceed to this section between these thick lines here, the parallel section. If the filter is not in filtration mode or wasn't in filtration mode when the wash mode was called, then we don't need to worry about shutting it down because it's not running anyway. So that brings us down to here as well. So before we run through the actual main sequence, let's just have a look at the fault shutdown requirements. So if a fault shutdown is required, what do we need to do? All we do is raise a fail to wash alarm, and then we follow this line down here where we initiate a fault shutdown. So this sequence isn't actually, or the sequence diagram isn't actually detailing what needs to happen as part of a fault shutdown, but essentially we just need to close all the valves. There's no pumps involved in this particular design. It's all gravity fed valve systems, so we just need to shut the valves. So that brings us to our main sequence here, which is, again, a little bit more complicated than the last one. But if the filter is above the weir level, so if we cast our minds back to the diagram right at the beginning of the course, there is a wash weir, which is about 1/3 of the way up the filter, and that stops the media, the actual sand, the filtration media, from being washed away during this process. So it's a little wall that stops the media from being washed away. If the level is higher than that wall, if we were to run the backwash sequence and allow water to flow the wrong way through the filter to clean it, the sand would lift up into the space above because there's water level higher than the weir, and then wash over the weir, and we'd lose some of that media or all of it if it carried on for too long. So if it's higher than that weir, we need to drain down through the waste valve. And when we drain down through the waste valve, we are draining down to a weir level, because if the waste valve is open, the water can only come down to the weir level anyway, because the waste drain is on the wrong side of the weir. So we can open the valve and then just do a check to make sure, are we at the weir? So you can keep going around in this little loop here. As soon as we're no longer above the weir, we do the check to say, are we below the wash limit? So is the level too low? So that captures the other way round of, we don't have enough liquid in the media to perform the air scour to disturb the media, because the media still needs something to be in to move around. So if that's the case and we're too low, then we need to fill through the inlet valve. And when we fill through the inlet valve, we just keep going around in this circle until we're, again, not higher than the weir. We haven't filled it too much, but we're now above the low level wash limit. Once that happens and we're happy with our level, we then open AVO5, which is our washout valve, the drain valve, which, to be fair, would already be open, most likely if you've had to do one of these anyway. Once it's confirmed as open, we then start the actual wash sequence, which consists of an air scour to disturb the media. And we do that by opening AVO4, which is our air scour valve. We run that for a timed period, and then we close AVO4, and that is the air scour complete. We then move into our backwash stage, where we pass clean water through the filter backwards to lift out all of the dirt that we disturbed with the air scour. And what that does is lift the level up and over the weir, but only just over the weir. So any heavy media, the actual sand that we're using to filter the water, wouldn't have enough uplift to get up high enough to come over the weir as well. So we open AVO3 for a set period of time, and notice that we don't close it once this period of time finishes. What we then do is open AVO1 to allow new water into the filter as if we were doing filtration, and that is called our top wash. So what that does is provide a cross flow across the top of the filter to push any scum or anything that's sitting on top of the water, or just below the surface of the water, towards the weir and out through the wash valve. By all means, go back and have a look at the pictures of the actual filter, so you can sort of match up what I'm saying with a visual representation of the filter. And then once the top wash timer is complete, we then move into the last phase, which is the rinse. And the rinse is designed to allow water through the filter in a normal way. So we're doing filtration, but it doesn't go out the outlet valve. It goes out of the rinse valve to waste. But we monitor what the quality of that water is. So that once it's ready to go out, once it's at a quality that it can go out of the outlet valve, we then switch over to the outlet valve and therefore finish our wash sequence. So we open MVO6, which is our rinse valve, for the start position. Once it's confirmed at position, we then close AVO5, which is the washout valve. This will allow our filter to start filling, because there's no other way out other than through the rinse valve. You need some sort of static head to push water through the media. So you'll see that the filter will increase in level until it starts pushing through the media. And then once that happens, all of the water is going through the rinse valve. So once the rinse timer is complete, we then do a check. Is our turbidity, which is a measure of how much dirt is in the water, is it at a healthy limit? If it isn't, then we restart the rinse timer, and that will continue until we can include a failure limit, which isn't on this drawing, but if it happens too many times in a row, then we deem that there's something wrong and too much dirt is getting through the filter, like after the wash, so something's wrong. But if the turbidity healthy limit is okay, then we start initiating our shutdown, which is close all valves, and then we do the check, which is important. Was the filter originally in the filtration mode? So that brings us back to here. So we set that here. Is the filter in filtration mode? We then do the check. Was it originally in filtration mode? If it was, then we need to tell filtration mode that we're now finished. Everything was okay, and it can continue doing what it needs to do. If it wasn't in filtration mode, then we can simply finish. and we've already shut all the valves, so we've already shut down. Wash mode is therefore complete, and that brings us to the end. Appreciate that is a lot to take in, and there might be an element of this video where you need to come back and keep looking at this. I will include this image in the area below the video, so whilst I'm talking through things, you can at least have a look at that image and see where we're going. But that gives us an overall idea of how this sequence is supposed to work. So just looking at the interface of the wash sequence manager, we have the same stuff that we had in the previous lesson for the filtration sequence, which is start, fault, normal shutdown. And we also have the same style start and shutdown manager. It just has some different interlocks in, and it also has a external wash required input, which you'll notice wash requested from filter. So that ties in with what we've just seen in our sequence diagram. Exactly the same thing on the interface as well, in terms of all of the assets that are required as part of this sequence are brought in through the interface via the in-out interface. And again, we're using alarm groups and alarm management. From an output perspective, slightly different, because what we have is individual sections, statuses for individual sections. So drain down active, fill active, air scour, backwash, all the areas that we saw in the sequence diagram. I have missed one here, which I will just add in now, which is our filter data, control statuses, and then wash cycle, wash sequence active. So if we jump in and have a look at the wash sequence manager, one of the first things you'll notice is obviously it's written in SCL, which is a textual language if you've never seen it before. In this sort of environment and what the use of this language, what we're doing with it, there is no great advantage in terms of writing in this sequence in SCL over ladder. SCL really comes into its own when you start doing loops with arrays and things like that. There's always a lot of what's the word I'm looking for? There's always a lot of arguments for using SCL over everything else, but the fundamentals of SCL are it should be easier to read than a graphical language, but the real sort of scenario is that a lot of people prefer ladder because it's quicker to diagnose issues with. It's easier to monitor. Monitoring an SCL is cumbersome. Just need to download that change that I made in the parent block, otherwise it won't let me go online. But yeah, I'll show you the monitoring now. It's not as nice as ladder. It's difficult to work with. So whilst I do like using SCL to write sequences, because as you'll see as we go on, like you can use the case statement and it's nice and easy to work with. From a debugging point of view, especially if you have a problem in a live bit of equipment, SCL can be a little bit more challenging in terms of being able to see what's happening, whereas you don't really have that problem with ladder. Ladder's very visual. So I'll leave this in our online and monitoring mode whilst we go through this. So at the beginning of our sequence, we don't have this in ladder because it's not needed because of the differences in the style of language, but we need to initialize our variables. So I'm initializing only when we're in the idle step. Filtration mode is set to false, and then I populate a variable called 0 with the value 0, so I can use the fill command to write 0 or false to every single request. So if I just show you where those requests are, this is all of our requests to say open AVO1 because it needs to fill, open AVO1 because the top wash is occurring, open backflush because open AVO3, sorry, because of the backflush is happening. So it's basically filling all of those with false if we're in idle, just to make sure that we haven't got any requests active. And you don't really need to do that in ladder because a coil is always scanned. Whereas if the case in our SCL language, if we've moved away from the case and we set something to true, it will still be true until it's set back to false, even though we're not scanning that case anymore. And that's something that you will get used to as you write SCL. If you've not worked with it before, it's very, very easy to accidentally leave something set to a value that you would expect to go back to false because you're no longer using it, but it doesn't. So yeah, that's something that's worth doing and worth remembering. And it comes with the territory of using SCL. You will come across stuff being set by accident, and the only way to fix something like that, if you're no longer scanning that case, is to have an initialization section that sets stuff back to what it's supposed to be when it's no longer needed. So we then have a region called shutdown checks, and all this is doing is checking the requirements. I can expand this here so we can see. It's checking these requirements, normal shutdown required, internal shutdown request, fault shutdown required. If any of those are true and our sequence is above the idle step, then we need to set the filter control status wash shutdown or shutting down, set that to true. And then the same for shutting down due to fault, but that one's only looking at if we're already doing a shutdown or shutting down, which was set up here. Then if it came from a fault shutdown being required, then we set the wash shutting down due to fault to true as well. And for those that are new to SCL, what we're doing is actually setting this variable here to the value of this expression. So wash shutting down and fault shutdown required. If both of those are true, then the result of that expression is true. If one of them is false, the result of that expression is false. So that's why you're not seeing true or false as the... you could write this as if washing shutdown and fault shutdown required are true, then set this value to true, or set it to false. You can still do it that way, but SCL becomes very cumbersome if you just use if statements everywhere all the time. You also then run into the issue that I mentioned earlier of forgetting to set it back to false if it's no longer required as true. We then come down to sequence control, and in sequence control what we're doing is using the case statement. So the case statement is a special instruction that looks at the value of a variable and then matches and executes the code that corresponds to that value. So we're saying if sequence has the value of idle, which is 0, if it has that value, then execute this section of code. So all it's doing is looking to start the sequence as long as we don't already have a active shutdown. And you can see here that sequence is then set to check current mode, which is started here, and that's then running this section of code. And what we're doing in check current mode, if we just jump back to here, is we're checking did it come from a filtration mode or has it come from the operator? That is the requirement to start. Has it come from the filter or has it come from the operator? So if we have an interlock active F001_1, and if I hover over that, it'll tell us what that is if I don't have it selected. So that is the wash sequence requested from filter. If that is active, then we set an internal flag local to this sequence that says filtration mode is active. And the only reason we do that is, just as the comment suggests here, if for whatever reason that interlock is not maintained and becomes false, well, we still want to do the checks because when we checked it, it was active, and therefore we want to continue doing the filtration checks. So if filtration mode active is set to true here. And then on this line here, so line 32, we then do the check to say if filtration mode is active, then check to make sure AVO1 is closed and MVO2 is reporting closed. The difference between these two is one is a modulating valve, MVO2 is a modulating valve, AVO1 is just a quarter turn valve. So this one will have a hard limit to say that it is closed, whereas this one is derived from the analog input, which is why they are slightly structured differently. Once we see that both those conditions are true, then we move on to check filter level. If filtration mode is false, so we'd fall to else here, we still check the filter level, but we ignore the condition of AVO1 and MVO2 because they're not required, because they're not actually in use. We then fall down to check filter level. So if we just come back to here, we are now at this section here, which is our check filter level section. And what we're doing here is saying if our filter level, ILO1, is above the at weir level, then a drain down is required. So set sequence to drain down required. Else if, and else if is not the same as else. Else if is only run if the preceding statement was false. So if this here is false, then we then check this statement. If this one is also false, then we run the else. So ILO1, if that's below the low weir level, then a fill is required. If neither a drain down required or fill required happens, then we would fall to else, which is open the drain valve. So drain down required, the level is above the weir, drain down to the weir using the washout valve. The first step that we do is make a request to open AVO5 because of drain down. So AVO5 drain down open, set that to true. And then what we do is we start checking the scaled level to see if it's below or at the weir level, which is the target level we're trying to achieve. If that happens, we then move on to open drain valve. Whilst this is running, we also execute a drain down timer, which we can see here. So drain down timer, if I just hover over that, you'll see that it's a TON. Doesn't do a very good job of explaining this to you, SCL, unfortunately, because nowhere there does it actually say TON for a TON timer. But if you have a look at the instance data, you can see that it's a TON time. So what we're doing is saying if the drain down request is open, then for filter data, set points, wash, max drain down time, run this timer for that max drain down time. If we get to done, then we set an internal shutdown request saying that the for the reason that the filter has been draining down too long and it hasn't achieved weir level, something must be wrong. So we set that internal shutdown request, and just to have a look at where that's used, if we come back up here, you'll see that it's used in the wash shutting down section. That internal shutdown request is there. That would set this wash shutdown to true and trigger a internal shutdown. Excuse me. Going back to what I said earlier about SCL, we would also need to reset the timer, because if we move away from this step, that TON timer will never be scanned again. And that means the next time we come to this step, because we set drain down open to true before this TON timer, the condition very well could be true already. So the timer could be done before it's even run, because it was done last time we visited this section. So always run a reset timer if you're moving away from the step that has a timer in it, unless you want to retain it, obviously. But a typical use case would be you're running a step timer to make sure that you're not in that step for too long. Once you've realized that you are in that step for too long, make sure you reset that timer before you navigate away from the step. Because this internal shutdown request has been set to true and we're shutting down, there is a step later on that moves us to a different step out of this case statement. So that's why we're doing the reset timer. So I know that's quite a lot to take in there, but what's happening in the correct sequence, if everything was to work correctly, we open the drain down valve, and then once we achieve our at weir level, which because we're not in this step at the moment, I can't show you what the levels are, but once we get to at weir level, we would then move to open drain valve, which is down here. And then nestled in the middle of those, we have our fill required, which is exactly the same as our drain down, but the other way around. So we ask AVO1 to open, which is our inlet. So allowing new water, dirty water, but new water into the sand filter. And what we're looking to do is to achieve the weir level. We can be above or equal to the weir level, and then we will move on to the sequence step, open drain valve. And we have the same TON timer and an internal shutdown request and a reset of that fill timer, exactly the same as the previous step to handle any faults. So now we're on to open drain valve. And this is where things are a little bit more complicated in terms of what we're doing, because we're starting to get into these different sections here. So we're now at this step here, open drain valve. So once the drain valve is step is active, we say AVO5 wash open to true, and we also set AVO5 drain down open to false and AVO1 fill open to false. And that handles the previous drain and fill commands if we have come from those steps. So we don't want to leave those valves open. And unlike ladder, where when we navigate away from a step with a coil on the end of it, that coil would return to false. That doesn't happen in SCL because we set the fill open to true. There's no conditional statement there. And if there was a conditional statement there, we're no longer executing this step anyway, so it's not getting scanned, so it would never get updated. So you have to manage the previous requests in the next step you've gone to. If you play with SCL and move this stuff around into different sections, you'll see what I mean. Hopefully that makes sense. But because we're if fill required was true and we'd set this AVO1 fill open to true, and that line of code there wasn't there, it would still be true when we're in the open drain valve. So you still have your inlet valve open, even though we're trying to drain the filter. And that's a problem. So you need to make sure that you handle those requests and set them back to false when they're no longer needed. So now what we're doing is confirming that AVO5 is open. If we come from a drain down step, it will be open already, so it will fall straight through this step. But it needs to make sure that it's got its open request. That's actually wrong there, because what I'm doing there is checking closed. That should actually be our open feedback there. Let me just download this so we can get back online. So as long as AVO5 is open, then we're okay to move on to our air scour step. And you can see here that I have a section, a comment section to say air scour. I could have actually used a region here, except for the fact that we are inside a case statement. And regions won't work when they're inside another instruction. It breaks the flow of the instruction and causes a compile error. So your only option here, as nice as it would be to use regions, your only option when you're in a case statement is to use comments to break out the different sections if you have sections like we do in our case statement. So now we're in air scour. We're doing the same thing, opening AVO4, so we set the request to true, and then you'll see a familiar setup of a timer and an action or a call to action using an if statement if that timer is complete. And what we're doing is opening the air scour valve. Once the timer is done, we then remove the request to open the air scour valve, set that back to false. We change our sequence step to the backflush, and we reset the air scour timer so that the next time we reach the air scour step, it isn't already complete. And we do the same, exactly the same setup for backflush, and we do exactly the same setup for top wash. The only difference is you'll notice that in the backwash section, we don't ask the valve to close. And that's because in our sequence diagram, we don't ask AVO3 to close. And we do the same in the top wash. We don't ask the valve to close. AVO1 stays open in accordance to the diagram. But we always reset the timer. And then we move on to our rinse section, which is probably the most complicated part of this wash sequence because it's the only place where our sequence can move backwards. But we handle it all in one step. So basically what we have is move MVO6 to the start position, and then we do the check to say if MVO6 is at target, which is the status that comes from a modulating valve once its actual position reaches a particular threshold of its targeted or control position. And we have the request coming from here to say it's at its start position. Then set the rinse count to 0. Set the PID control to true because we're trying to actually control a flow here. Set the start position back to false so we no longer continue resetting the rinse count, setting the PID control to true, and also then tell AVO5 wash open to be false. So as soon as we tell MVO6 to open, which is here, MVO6 to start position, we need to confirm that it's reached that position, which is the at target. And then once we've done that, we close AVO5. And then we won't call any of this section again because it cuts itself off from this, this check here to see if we're in start position. Because that's now set to false, this whole section here can't be true. I have just noticed an error in this logic here, which will be fixed when we do the example of this start position true. We'll set the start position every scan of this block whilst we're in the rinse condition. So we've got a relay chase style issue here of start position being set to true and then being set to false, and it will just keep flip-flopping between. But I'll fix that as part of the walkthrough that we do of live code with the HMI, so that's resolved. But hopefully you still see the type of structure that we're trying to set up here. We then have our rinse timer, exactly the same as all the other steps. Once the rinse timer is done, the first thing we do is reset the timer, and then we call the check turbidity levels, where we look at QiO4, and we say if the turbidity value of QiO4 is less than the filter data set points wash post-wash turbidity healthy limit, then the sequence must be complete because that's what we're looking for. We're looking for the turbidity to be below a healthy limit because the lower the turbidity, the cleaner the water. Otherwise, if it's not below that level, then we increment the rinse count to 1. And because we've already reset the timer, then this timer will obviously run again. And if the rinse count, then we do the check saying if the rinse count is over or equal to the max number of rinses before failure, if that condition is true, we initiate an internal shutdown request saying that everything has worked fine up until the turbidity healthy limit, the checks that we're doing for the rinse, and something is wrong because we've had to rinse for too long and too many cycles. So we must fail the filter and it needs to be manually inspected. At this point here, where we say sequence complete because we're below our limit, we then come down and we make a simple request to close all valves. So all of the valves get closed, and if filtration mode was active, tier portal deciding to just leave a tooltip there. If filtration mode is active, then we set filtration mode active to false. Again, important. If we don't do that, then we run the risk of leaving it as true. I know we do the initialization and set it to false up there anyway, but it's good practice to get in the mindset of remembering to set stuff back to false if it's no longer needed. And then we set the interlock F001_2 to true. And that interlock there is wash sequence requested from filter complete. And the filtration sequence will then pick that interlock up. It will also set it back to false. and allow the filtration sequence to continue doing whatever it was doing. So this sequence, the wash sequence, again, as we go through the course and we come to the actual examples, it will become a lot clearer because you'll be able to see how things are going in a real scenario, like as the filter calls for a wash and things like that. But this, when it's called from the filtration mode, it's an interrupt sequence. So the sequence is running in the filtration mode. That sequence doesn't stop, it just pauses, sets an interlock, which tells this one to start, the wash mode to start. The wash mode completely finishes its cycle and then sets another variable, another interlock, to tell the filter sequence that this one completed successfully. If it completed successfully, the filtration sequence then sets those interlocks back to false and continues with what it was doing before. So they are loosely coupled. They're coupled through two variables that are allowing one to stop and another one to start, and then a reporting variable that says, yes, I finished correctly, so the other one can continue. And that's a really good way of being able to be sort of fluid with interruptible sequences. And down here, finally, we have our shutdown management, which again is a little bit different. I could have put this in a function block, in its own shutdown function block, but it's really, really simple in this case. It's just we need to shut all the valves. So if our wash shutting down value is set to true, then request shutdown close all valves. And we then wait 10 seconds to allow all the valves to close. And we also set a fault shutdown alarm. And then once the shutdown timer is done, we reset it. Always make sure that we reset because this is called inside an if statement. If we didn't reset this timer and the next time the block was scanned and this variable was false, the timer's last known status is complete. So this here, shutdown timer done, would still be true if it's a static. It's not though, it's a temporary, but it would still be true. This instance data will still have Q as true. So once the shutdown timer is done, reset the timer and set the sequence back to idle, which takes us right back to the top of the sequence where we are waiting for an input to start. So it's a really, really long walkthrough. Sorry about the length of this, but hopefully you can see the structure of SCL and how we're using a management instruction, which is case structure, to actually segregate and manage each individual case. It's no different really to what we're doing in ladder, except for the fact that every single step in ladder is scanned and every single output request, like a coil, for example, is still processed like normal. Whereas in SCL, if we're not on this complete step is not scanned at all. So anything that was set on the previous one will just remain in that state unless it's used elsewhere. And that is a really, really important factor to remember when you're writing anything in SCL, that SCL effectively skips over code that's inside if statements, inside case statements, inside there's lots of different other statements that cause similar effects. So it's important just to remember that when you're writing. But from a logical output point of view, everything is exactly the same as how it would operate in ladder in terms of looking from an outside perspective in the main block that calls this. They don't look any different in terms of what they're doing. One thing that I have missed on the interface of this is the actual output commands for the valves. I'll fix that before the next video, because in the next video we're going to have a look at the request feature that I build into all of my sequences. And basically what that is allowing more than one request to control one asset, whether it's from the same sequence or a different sequence. But that we'll go through that in the next lesson.